Hello folks, welcome to the next episode of Electromagnetism. Today we're going to begin with a lecture on how to find the energy in an electrostatic charge distribution. Let's begin with the following. We know that work is intimately related to energy by the work kinetic energy theorem. And we know that work is defined as F dot dx as we go from some initial point A to a point B. Now, in classical mechanics, it's common that work is done against an object such as gravity, right? So if you're lifting up a box using your hands, you're working against gravity to lift that box up. But what are you working against in electrostatics? Well, consider the following situation where you have a few charges Q1 and Q2, and you're trying to bring in a third charge, Q3, from effectively spatial infinity. So we have two pre-existing charges Q1 and Q2, and we're trying to bring in a third charge from very, very far away, effectively infinity. Now, of course, as I try to bring in this charge, let's say all of these guys are positively charged, it's going to take some energy to keep that charge in, and actually to bring that charge in and keep it there, it's going to take some energy, right? That's what we're doing work against, the pre-existing electrostatic field. And we know that in electrostatics, force is simply QE, right? The charge times whatever electric field that charge is situated in. Now, since we're working against the electric field here, I'm going to put a minus QE so that we can write the work is minus Q times the integral of E dot, instead of X, let's say we're displacing the charge in an arbitrary direction or along an arbitrary path DL from some initial point A to B. Let's say this is our A and this is our B. Well, this may look familiar. Minus the integral of E dot dl. What is the integral of E dot dl? Remember that because the curl of the electric field was 0, we were able to define a scalar potential function, the electric potential function, whose negative of the gradient was the electric field. And to go from the potential to the electric field, all we needed to do was E dot dl as follows, right? So the electric potential was simply the integral of the electric field, and the electric field was simply the gradient of the electric potential with a factor of a negative sign. And so in this case, this is simply the electric potential right here. This is simply Q V of B minus V of A, which I may simply write succinctly as QV. So this is the work or the energy needed to bring in a charge with a magnitude of Q into an existing electrostatic distribution with a potential of V. This is the formula that we will use throughout today's problem solving. But there's one more idea we need to encounter, and that is, what is the work needed to assemble a distribution of point charges? This is the work needed to bring in a point charge into an existing distribution. But how much work would you need to build that existing distribution in the first place? Let's check that out. Let's say we have the following charge distribution made out of 3 charges Q1. What is the work needed to assemble this charge distribution? Well, first let's consider the amount of work needed to bring Q1 in. Remember that we found that work is given as QV. So focusing on Q1, we would have Q1 times the potential due to this charge and the potential due to this charge. So let's write that down. The potential due to this charge is going to be Q3 over 4 pi epsilon naught and times the distance between the two charges, R13. Now this is the potential due to Q3, but what about the potential due to Q2? We've got to also factor that in. Now, because this factor of 1 over 4 pi epsilon naught will be repeated, I'm going to factor that out so that you have the following. Q1, Q3 over R13 plus Q1, Q2 over R12. But now, remember that we want to find the work needed to assemble the entire distribution of charges. So we also need to account for what if you brought in Q2 into this distribution, right? Well then Q2 would face resistance against 1, 3. So let's factor that in. So we have the pair of charges 1, 3, 1, 2. Now we need to put in the pair of charges 2, 3. And so this is the total amount of energy or work needed to assemble this charge distribution. And likewise, if you wanted to find the amount of energy needed to assemble an arbitrary charge distribution, you would have to take each one of the potentials and pairwise potentials, add them up as such, and multiply, of course, by 1 over 4 pi epsilon naught, and the charge of interest. Okay. Commonly, you will see that the formula is written as 1/2 times the sum of over all the charges and all the potentials, Qi V R sub I. So we have, once again, pretty much the same formula, the charge times the potential, but now we have a factor of 1/2, and that's because of a little mathematical trick that lets us count all the charges. So charge 1, charge 3, charge 3, charge 1, charge 1, charge 2, charge 2, charge 1, charge 2, charge 3, charge 3, charge 2. But now you can see that, of course, these two are the same, and this pair is the same, and this pair is the same. So we're just double counting each pair, and so to actually count the actual number of pairs, we divide by half, right? So that's why that factor of 1/2 exists, just as a mathematical convenience. But the main idea is the same. You take the charge multiplied by the potential of interest. Okay, and that is another very key formula. Work is equal to half QV. And this is the amount of energy you need to assemble an entire point charge distribution. But what if you have a continuous charge distribution? Well, it's very easy to modify this formula now. Instead of Q, you may now write that the work is 1/2 rho d tau times V. And rho d tau, that gives you your Q, your total amount of charge. So, in essence, you have the same formula, but now for a continuous charge distribution. Now let's check out the problems for today. Here is another view of problem 1. Let's take a look at problem 1. Here is the first part of our first problem. A uniformly charged spherical shell of radius A and total surface charge Q exists in a vacuum. Part A. Use W equals half VQ to calculate the electrostatic energy in the shell. Let's start with that. Here is our uniformly charged spherical shell, which has a radius of A and a total surface charge of Q. We need to use this formula. The work is equal to half V or dq to find the total amount of energy in this electrostatic charge distribution. Now, we derived or informally derived this formula in the lecture of this video, so you can go ahead and watch that if you'd like a review for this. But now we're just going to find the potential of this sphere and then plug that into this formula to determine the energy for this charge distribution. So first, as always, when we have something like this, let's consider the scenario. First things first, we need to determine the potential. To determine the potential, we might start from the electric field and then integrate and then negate that to get the potential. But hold on to your horses, because there's a much easier way to determine the potential. Due to the shell theorem, we can simply consider this a single point of charge with a magnitude of Q. And so the potential outside will simply be the potential for a point charge, which would be Q over 4 pi epsilon naught R. And the potential inside would simply be this potential, but stuck at the radius. So Q over, is this capital Q here? No, it's lowercase q. Surface charge lowercase q over 4 pi epsilon naught A. So here's the potential inside, here's the potential outside. Since we are asked to calculate the electrostatic energy inside the shell, we will use this potential and simply plug in. So we would have half, here's our V, q over 4 pi epsilon naught a, q over 4 pi epsilon naught a times q, right? Since we have dq, but we're summing over all the charge, giving us q, gives us q squared over 8 pi epsilon naught a. Not too shabby. Part B asks us to use the second formula for determining the energy of an electrostatic system, which is the work is epsilon naught over 2 times the integral of the electric field squared over all of space. Now, we did not see this formula in the lecture of this video because it's a bit harder to derive, but it comes straight from this original formula. So let's go ahead and use it. First, we need to determine the electric field in all the areas of space. Now, since this is a spherical shell, there is no electric field inside the shell because there is no charge density, right? We know from Maxwell's equations that the divergence of the electric field is the charge density over epsilon naught. If there's no charge density, there's no electric field, but that doesn't necessarily mean there's no electric potential. So you got to be careful with that. So the electric field inside is 0. What about the electric field outside? Well, that would be the electric field for simply a point charge, which is q over 4 pi epsilon naught r squared. So let's go ahead and use this formula. We're going to have epsilon naught over 2. We're going to expand this integral. First of all, dv is 4 pi r prime squared. And then we're going to have the electric field inside r less than a, because a is the radius, and then dr prime plus the integral of this exact same thing, but as the electric field is greater than a, dr prime. Okay, now we know the electric field inside is nil, right? Since it's a shell, there is no electric field inside, hence this whole first term goes to 0. We may now turn our attention to the second term, so that the work is equal to epsilon naught over 2 times this mess, which is the integral of 4 pi r prime squared. What is the electric field outside? It is this, but it is squared, right? I neglected to put the square symbol. So let's go ahead and square this. So I would have q squared over 4 pi epsilon naught all squared times r squared, which would be r to the 4th, or r prime to the 4th rather, dr prime. As I go from r prime is starting from the outside of the shell, which is a, to infinity. To infinity and beyond, as they say. So here you notice that I have 4 pi epsilon naught, and I have a 4 pi epsilon naught here, canceling out that factor of 2. Let's bring out all the constants outside, so that we have q squared over 4 pi epsilon naught times 2, which is q squared over 8 pi epsilon naught. And now we're going to integrate. R prime squared over r prime to the 4th just leaves r prime squared on the bottom denominator there. So we're going to have the integral from a to infinity of 1 over r prime squared dr prime. Now, you may be used to seeing this integral, but let's go ahead and evaluate it. This is simply going to be, I'm not sure if you can see as far below as there, but this integral right here is simply going to be, let's write it here, minus 1 over r prime, as r prime goes from a to infinity. So this is going to be minus 1 over infinity minus 1 over a, giving us a positive 1 over a, and thus leaving us with the following energy. This is equal to q squared over 8 pi epsilon naught a. And there you go. We get the exact same energy in 2 different ways. Now let us consider the third part of the first problem. See, what is the amount of work dw required to bring in a charge dq prime from spatial infinity to the surface of the shell if the shell has a total charge of q? Integrate dw from q prime is 0 to q prime equals q to obtain the total work to charge the shell. Let's go ahead and find what this total work is. I'm going to... Okay, so the amount of work dw will simply be half of q dv. Oh, sorry, v dq. V dq. Or should I say q prime? As q prime goes from 0 to Q. So what is V? Well, the potential for a point charge is simply Q over 4 pi epsilon naught. So we're going to have Q over 4 pi epsilon naught R dq prime as Q prime heads from 0 to Q. Now, since we're on the surface of the shell, I'm going to make R equal to the radius of the sphere, which is A. And so this is going to give us nothing but Q squared over 2. Oh, sorry. There should not be a factor of half here, but since we're integrating, we'll get that factor anyway. We'll get Q squared over 2 times 4 pi epsilon naught times A, which gives us, once again, the same work, Q squared over 8 pi epsilon naught A. And there you go, folks. That's how you obtain the energy for this electrostatic charge distribution, which in this case is a continuous distribution. It's a spherical shell in 3 different ways. We found the energy using work is half of VQ. We found the energy using the electric field. And finally, we found the energy by slowly integrating over the total amount of charge on the shell. Now let's check out problem 2. Here is the problem. Now let's examine the second part of problem 1. Here is the second part of problem 1. Now a non-relativistic particle of charge E and mass m is fired with velocity v directly towards the charged spherical shell from very far. If Q and E have the same sign and v is a very small velocity, what is the distance of the closest approach between the charge E and the center of the shell? Let's first draw a diagram to illustrate the situation at hand. What we have is some small particle of charge Q and mass m of charge E and mass m hurtling towards our charged spherical shell, which has a total charge of Q, but the velocity with which this charge is heading is much less than c. So it's non-relativistic. Now, if Q and E have the same sign, then we expect that at some point the charge is going to get close, and then turn back. What we have to figure out is the distance of closest approach between the charge and the center of our shell. So, how can we solve this problem? Well, one thing we could do is consider the forces at hand. As this charge gets closer and closer to the spherical shell, the force on it is going to get stronger and stronger. So it's going to have an electric force exerted on it that is at first weak, but then grows stronger. This is F sub E. And we know the electric force is Q times E. In this case, of course, Q is small e, and E is the electric field due to this spherical shell. Now we could go ahead and find what this force is, but of course this force is changing with time. It's much like the force from a spring, which is not constant. And so it's a bit troubling to use the force. That's why we turn to energy in this case. Initially, the charge has what? Does it have potential or kinetic energy? Well, I'm not quite sure, but I do know that when the charge is ready to turn back around, it has no kinetic energy there for sure. So that means it must have only potential energy here and only kinetic energy initially. So conservation of energy tells us that all of the kinetic energy turns into potential energy. In other words, half mv squared turns into EV, where EV is the potential energy for this charge. If you're wondering how I got EV, well, take a look back at your old electromagnetism notes, and you'll see that EV gives us the amount of kinetic energy for a charge. So now all we have to do is plug in our numbers. So the potential energy, the electric potential for a charge, for a point charge, is going to be E, or rather we want the potential from this, not the potential of the charge itself. Q over 4 pi epsilon naught R, not R squared. I almost wrote that down instead. And now all we have to do is solve for R. So let's go ahead and do it. All I have to do is move all the other terms to the other side. So I'll have mv squared over 2qe, and I'll have 4 pi epsilon naught as well over here, so 4 pi epsilon naught, and all of this is equal to the distance of closest approach. And that's how you solve the second part of problem 1, conservation of energy. Here is the problem. Let's check out problem 2. Alright, let's check out problem 2. Two coaxial cylinders of radii A and B and length L carry charges plus Q and minus Q spread uniformly over their surfaces. Part A asks us to find the energy stored in this arrangement by integrating the following equation in the region between the cylinders. Well, as you can see, the equation we need to find the energy for this electrostatic distribution involves the electric field. So we need to find the electric field for this charge distribution. Let me write this equation down. Work is equal to epsilon naught over 2 times the electric field squared integrated over the entire volume of free space. So let's find the electric field everywhere in free space. So first, what are our regions? Our regions are inside the small cylinder, between the two cylinders, and outside the entire charge distribution. Now outside the entire charge distribution, that part is a bit easy because this inner cylinder has Q, total charge, and the outer cylinder has a total charge of minus Q. So the net charge is 0, hence the net enclosed charge is 0, and so the electric field should be 0 outside the entire charge distribution. What about inside A? Well, are we told that these are cylindrical shells? If so, then inside A there should be no electric fields either, unless there is some volume charge density. So let's see. The charges plus Q and minus Q are spread uniformly over the surfaces. Hence, these are surface charges, and there is no volume charge density inside of the inner cylinder, hence giving us an electric field of 0. So be very careful with your reasoning. If they said you spread uniformly over the volume, then you'd have to be careful. Then you would have to do Q over the volume of the cylinders, which would be pi A squared over L. Pi A squared L in the case of the inner cylinder. But in this case, we know that these are only surface charges, hence there is no inner electric field. Now, all that is left to determine is this middle electric field. So let's go ahead and do that. How can we determine the middle electric field? Well, in this case, do we have an infinite charge distribution or an infinite cylinder which we can use for Gauss's law? Well, in this case, we are told that these two cylinders both have a very finite length of L. So Gauss's law may be out of question. So what can we do? Even though this is a finite cylinder, however, we are entitled to use Gauss's law because I totally forgot to write it down in the problem description, but it says to neglect end effects. So we can effectively treat the cylinder as if it were infinite. So let's use Gauss's law, which tells us that the dot product of the electric field with the unit normal area vector is equal to the charge enclosed over epsilon naught. So let's create a charge distribution as follows, a Gaussian surface as follows. So we'll have some kind of a cylindrical Gaussian surface like this, and it'll have some kind of a length, or otherwise we can enclose the entire length if we so choose. So let me say that this is the length of L. Even though it does not look like it, it is not drawn to scale. Now, what is the surface area of this charge? Well, it would simply be the surface area of this Gaussian surface is going to be 2 pi r times L, capital L. That's going to equal the charge enclosed. Now, what is that? That's going to be Q, which is the total charge over epsilon naught. And so, at this point, I may simply solve for the electric field, which is going to be 2 over 2 pi r L epsilon naught r hat. And there you go, ladies and gentlemen. We have just figured out the electric field in all regions for this charge distribution. have just seen me erase a good part of my work for this problem. The reason why is because I screwed up the integration volume element for a cylindrical surface. Instead of putting dr d theta dz, I put dr d theta d phi, which is what the three variables for spherical coordinates are, not for cylindrical. So let's remedy our work this time. We're going to have the total energy is going to be as follows: epsilon naught over 2. D tau is going to be r d theta dr dz. This is the volume element for a cylinder. Now I'm going to put prime on all of these variables since we're going to be integrating them throughout. And what is E squared going to be? It's going to be this thing squared. So Q squared over 2 pi r L epsilon naught squared. 2 pi r L epsilon naught squared. R prime squared. So that's what we have. Now let me bring out all of my constants outside. So I'm going to have Q squared epsilon naught over 2 times 4 pi squared L squared epsilon naught squared and times the integral. R prime and R prime cancel out so that I simply have 1 over R prime dr prime d theta prime d phi prime. Now R prime is going to go from the inner to outer radius, A to B. Theta goes from 0 to, now I should use, see again I messed up my variables. This should be phi, this should be phi, this should be z. So phi goes from 0 to 2 pi and z goes through the length of the cylinder. So I'm going to have the energy for this electrostatic charge distribution is going to equal Q squared epsilon naught. We can simply quickly integrate phi and z since they don't make any appearances in the integral, so they give us 2 pi L over 2 times 4 pi squared gives us 8 pi squared L squared epsilon naught squared. Okay, and 1 over R prime dr prime, that's going to give us a factor of ln of b over a since we integrate from a to b, the upper limit over the lower limit. Now let's make some simplifications. Pi goes into pi squared once, L goes into L squared once, epsilon naught goes into epsilon naught squared once, 2 goes into 8 4 times I suppose, so that our total energy is Q squared over 4 pi L epsilon naught. 4 pi L epsilon naught. There you go folks, that is the energy for this electrostatic charge distribution. Now let's consider the next part of this problem, which asks us what is the capacitance of the cylinder. Remember that capacitance C equals Q over the electric potential V. What is the electric potential in this case? Well, assuming that spatial infinity is our ground, what is our electric potential? Well, we simply need to integrate the electric field here and negate it to get our electric potential. So we're going to get, if we integrate this, this is going to give us, where are we going? Well, we're integrating from the inner radius to the outer radius. So this is going to be the integral minus the integral of from a to b of q over 2 pi L epsilon naught 1 over r dr. Let's put primed on these variables since we're integrating them throughout. So this is going to simply be q over 2 pi L epsilon naught ln of b over a. Don't forget your minus sign over there. So now that we have this, we may simply substitute this in. So this is going to be q over all of this nonsense. Now if I do that, I'm going to have q over minus q over 2 pi L epsilon naught times ln of b over a. Now, whoops, this ln of b over a should be here. Should be making an appearance on the denominator. Now q and q cancels out, and so I'm left with my capacitance for this cylinder. Hopefully you can still see down here is minus 2 pi L epsilon naught times the natural log over the natural log of B over A. And there you go. That's the capacitance. One small mistake is that there should not be a negative sign over here for the capacitance. Now let's check out our third problem. Here is the problem. Let's check out problem 3. Alright folks, let's check out problem 3. A spherical cavity of radius A is hollowed out from the interior of a solid neutral conducting sphere of radius capital R. At the center of the cavity, a distance A from the origin along the y-axis, a point charge minus q is placed. Part A. Find the surface charges sigma sub A. I guess that's what you call this symbol. I still don't know to this day. Sigma sub A and sigma sub R. Okay, let's do it. Well, this right here is a spherical cavity inside a solid neutral conducting sphere. Okay, so now we have entered the world of conductors. Conductors are objects such as metals where the electric field inside this object is 0. The charge density is 0. All of the charges that a conductor will ever have will reside on its surface. And this is a very magical fact, but as it so happens, this is the case in reality. Now, here in this case, we not only have a conductor, we have a cavity inside this conductor. And furthermore, inside of this cavity, we have a negative charge placed inside. Because of this negative charge, the conductor will quickly act so as to keep the electric field inside of it 0. But how can it keep the electric field inside of it 0? Well, it can put some agents. It can put some agents of positive charge outside this cavity to counteract this negative charge. And in fact, how much positive charge does it need to put around this cavity so that the total electric field at any point inside the conductor is 0? Well, it needs to put a total amount of plus q charge on the outside of this cavity to counteract this minus q inside, so that the electric field is still 0 inside the conducting sphere. And so hence, the surface charge density outside this cavity is going to be positive q over 4 pi a squared, where a is the radius of this cavity. That right there is the surface charge density on the cavity. Now, what is the surface charge density on the whole sphere? Well, because there's a plus q here, well, what's the charge going to be on the outside? Well, originally, this was a neutral conducting sphere, right? So the charge on the outside was perfectly balanced. But now we've robbed it of some positive charge to bring them on to the surface of this cavity. So outside, on the surface of this conductor, you're actually going to have a total net charge of minus q. And so the surface charge of the whole conductor is going to be negative q over 4 pi capital R squared. That's part A. Part B asks us, what's the electric field outside? Well, now that we know the total surface charge outside the conductor, it's quite easy. The electric field outside will be simply that of a point charge with magnitude minus q, which is going to be minus q over 4 pi epsilon naught r squared. And of course, it is in the r hat vector. Now, at this point, I should point out one thing. There's another way you could write out this electric field, and that is rewrite the radial direction as a combination of xi hat, yj hat, zk hat. It's the exact same answer, but written in just a slightly different way. So 4 pi epsilon naught x squared plus y squared plus z squared to the 1/2 on the denominator, and xi hat plus yj hat plus zk hat on the numerator to tell us which way the electric field is pointing. Now let's write down the electric field inside the cavity, which is going to be the exact same as that outside the entire conductor. Now, of course, if I write it out in terms of vector notation, it's going to look slightly different, because now, where's our source charge originating from? It's originating from somewhere that's not the origin. So that's how I'm going to write it. I'm going to write minus q. It's still going to be pointing radially outwards. So I'm still going to have xi hat, yj hat, ck hat over here. But now my source charge is originating from somewhere that's displaced from the origin. Hence y plus a squared plus z squared to the 1/2 power. That's the difference that this charge makes. And this should also be y plus a, as it turns out. Y plus a j hat. Y plus a j hat for the y component right here. And now let's take a look at part D. What is the force on the charge in the cavity? Well, the charge in the cavity experiences no force whatsoever. This is a neutral conducting sphere. There's no electric field inside, and there's no charge exerted on the charge in the there's no force exerted on the charge in the cavity. So the answer to part D is there is a force of 0 on the charge in the cavity. Finally, part E, which answer would change if another charge was brought near the conducting sphere? If another charge were brought near the conducting sphere, let's say a charge q prime, then you can imagine that the surface charge density on the outer conducting sphere would change, but the surface charge on the inside, the surface charge density on the inside, on the surface of the cavity inside would not change, because there's a total disconnect between the cavity surface and the conducting sphere surface. Why? Well, because the electric field is 0 inside. So there's no way any charge that's brought near the conducting sphere on the outside can in any way influence anything on the inside. So if another charge were brought near this conducting sphere, the only thing that would change for part E, the only thing that would change is the surface charge density on the outer conducting sphere and the electric fields outside. The electric fields outside the entire conducting sphere, which makes sense, right? If the surface charge density changes, so should the electric fields outside the entire conducting sphere. So folks, that's it for today's lecture. We'll see you next time.